very much, Robert. Got it. And thanks to all the organisers for inviting me to speak here at this British Combinatorics Conference. I'm particularly pleased that I'm able to speak at the Durham conference because I spent 6 months on sabbatical based out of the computer science department at the University of Durham in 2012, and I had a really lovely time. Okay, so I'm telling you about generating graphs randomly, and I thought we'd start by imagining a conversation between a combinatorialist and a computer programmer over a coffee or hot beverage of your choice. So the combinatorialist is actually a random graph theorist and says, let G be a graph with degree sequence k1 up to kn chosen uniformly at random. And they're about to say some nice things about this random graph, but the programmer says, wait, stop, how would I choose a random graph with the given degree sequence? And then they both sort of blink at each other for a while as they adjust to each other's perspective. So it is a very different problem to try to come up with a uniformly random graph with given degrees. And so, yeah, there's not much about the properties of such a graph involved. Of course, it's easy to generate from some families of graphs. So if you just want a graph with n vertices and you don't care about anything else, you can simply flip a coin for each possible edge and put the edge in if the coin comes up heads. That's the uniform random graph model. And it's also an algorithm. It's easy to generate a uniformly random graph with a given number of edges. You just put all the edges in a bag and you uniformly choose one from the bag without replacement until you have m edges. That's also an algorithm. However, if you're looking at generating graphs with a given degree sequence, it's no longer so easy. And this is basically because your edge choices are no longer independent. So if you fill up enough edges around a vertex so that it has the desired degree, then you know that you're not going to add any more edges at that vertex, for example. So it becomes a more challenging problem. And this is the problem that I'll talk about today. We also restrict ourselves to graphical sequences. So let's say a sequence of positive integers, which is the degree sequence of some graph. So my graphs are all finite, labeled with the vertices 1 up to n and simple. And I don't assume that the degrees have been sorted into non-increasing order or anything. It's just a sequence of numbers, and the jth vertex should have degree kj. I'll often just say degree sequence when I mean graphical sequence. Given a sequence, we can test whether it's graphical quickly using the Erdős-Galai conditions or the Havel-Hakimi algorithm, which also gives you a realization. Okay, so for a graphical sequence, k, we can let g of k be the set of all graphs with the given degree sequence, so on the vertex set 1 up to n. And if k is a regular sequence, we'll just write gnk to emphasize that it's regular. Okay, so we really don't just have one degree sequence or one set of graphs. We want to talk about the asymptotic behavior of these algorithms. So you should think of a sequence of degree sequences, k of n, k1 up to kn of n. It has length n, but also the elements of this degree sequence might themselves be functions of n. And we want to assume that this is a graphical sequence, maybe not for all n, but for at least some infinite subsequence of n. For example, if you want cubic graphs, you need n to be even. So as long as we have some infinite subsequence of the natural numbers that we can use to take the limit as n goes to infinity. However, this notation is clunky and not very nice, so we usually suppress this dependence on n, and I just write the degree sequence like this, but I'm really talking about a sequence of graphical sequences. Okay, so now we can talk about our aim. We want an algorithm for producing a graph from this set of all graphs with the given degree sequence, which has a guaranteed distribution which is either uniform or close to uniform in a sense that we'll make precise soon. And it should have a guaranteed upper bound either on the runtime or on the expected runtime if the runtime itself is a random variable. Okay, and of course, from a theoretical computer science perspective, any polynomial bound on the runtime is good, but low degree polynomial bounds are obviously better, especially because, as we all know, there are real world people out there who are using graphs to model their system of interest, and these networks can get really big. So we do want efficient algorithms. Okay. And there are 4 main approaches to this problem if you restrict yourself to algorithms that have been fully analyzed. There's the configuration model, sequential algorithms where graphs edges are added in one by one, switching-based algorithms, and the sort of Markov chain Monte Carlo sampling approach. And I'll be discussing 3 of these today. Some of these algorithms give you precisely uniform output, namely the configuration model and the switching-based algorithms. Now, the caveat is that this assumes that you have some perfect source of randomness sitting in your office, some radioactive rock, right, that you're getting your uniformly random bits out of. But assuming you have that, then this really does uniform random sampling. Other algorithms might be approximately uniform or asymptotically uniform. So the sequential algorithms are asymptotically uniform, which means the distance from uniform tends to 0 as n tends to infinity, but you can't make that distance any smaller by, let's say, running your algorithm for longer. Whereas a Markov chain algorithm, the user can specify some tolerance epsilon, and you can make epsilon smaller by making the runtime longer. So you can get within epsilon of stationarity, of uniform, and make that epsilon smaller by running the algorithm for a bit longer. So there's a sort of different notions of being close to uniform. Okay, and as this is the one that unfortunately I won't get time to talk about today. Now, the stuff on this slide you don't really have to absorb in full. This is just telling you how I'm measuring my distance from uniform. So a metric on the set of all probability distributions on a finite set omega is the total variation distance, which is a half of the 1 norm. That's a convenient metric to use. And here is a bunch of standard asymptotic notation. So just quickly, f is little o g if f divided by g tends to 0. F is big O of g if eventually the absolute value of f is bounded above by some constant times g, and we assume here that g is then positive eventually. And if f is big O of g and vice versa, then we write capital theta for this. Okay, just standard stuff. Okay, so it's time to talk about the configuration model, which was introduced by Bolabaj, and it also came up in the asymptotic enumeration work of Bender and Canfield, and Nick Warmold's thesis, I believe, was the first place where it was written down explicitly as an algorithm. And many of you will find this familiar. So we start with n cells, and the jth cell has kj points. So these are numbered 1 to up to n, let's say, and the points are distinguishable. So each point has a name and we can tell them apart. The total number of points is the sum of the degrees, which is twice the number of edges that we want to have in our graph. We choose a uniformly random partition of the m points into pairs, and that's easy to do in order m time. And this is called a uniformly random configuration or a pairing. So one of these is a configuration or a pairing. Then you just shrink the cells down to vertices, and what you will get is a multigraph with the correct degree sequence. So we see that this one has a loop and this one has some repeated edges, and I don't want that. So I'm going to just reject this because the output graph is not simple and try again. You choose another uniformly random configuration and take the corresponding graph, and you keep doing that until you find a simple graph. Okay. So this is a very nice algorithm, and the reason why it works is that every graph in G of k, which is then simple, arises from exactly the same number of configurations, this many. So if your configurations are random and you condition on being simple, then your output graph is also uniformly random, which is the reason why we like it so much. People use the configuration model to do calculations in, and it's also an algorithm. Okay. So choosing each configuration takes order m or theta m steps. And how many do you need to generate until you get a simple one? Well, that's a random variable with expected value 1 over the probability that a uniformly random configuration is simple. It's just a geometric random variable. And you can analyze this probability very precisely. in particular, the maximum degree is, if the maximum degree is the order of square root log n, then the expected runtime will be polynomial in n. And we can say more precise things than this. So this means if your maximum degree, I'm obviously here using Kmax to indicate maximum degree. If it's pretty small, then you probably want to use the configuration model to do your sampling, and that's going to be good enough. But if it's growing any faster than this, you'll just reject way too many times and you won't get a polynomial expected runtime. Okay, excuse me. Second. Thank you. All right. Now we're skipping right over section 2, which was switching-based algorithms. Sequential algorithms, and we're going to switching-based algorithms. Right. We just saw that in the configuration model, if there was any problem whatsoever with the configuration that you chose, you throw it out and start again, even if it's just going to give you one double edge or something. And this sequence of work starts by asking the question, isn't this a bit wasteful? If there's only a few problems, can't we just work on them and you know, not have to throw it out each time and start again? So McKay and Warmold had the idea in 1990 to combine the configuration model algorithm with ideas from the switching method for combinatorial enumeration. And I'm going to tell you about this method. So switching usually is a small local change that you make in some combinatorial object to remove a defect usually in a fairly controlled way. I'll explain a bit more. Here is a picture of a setup that you might use to try to remove double pairs in a configuration one by one. So what I want you to think of here is that I have 6 different cells. These are all distinct. There's exactly 2 pairs between these 2 cells. So the multiplicity is 2, and exactly 1 pair here. That's going to be a simple pair, and same over here. And then I'm going to replace these 4 pairs like so that every point is still paired up. And I only do this if each of these 4 pairs is also simple. So there shouldn't be any pair already between these 2 cells. Of course, all of the cells in the picture might have lots of other points, but they're going to other places. The pairs that we've shown here are the only 2 between these 2 cells, for example. Then when you choose this as carefully as I've explained, you're removing exactly the double pair that you're targeting. You're not removing any other sort of defects, and you're not introducing any problems. You're certainly not introducing any loops because the cells are all distinct. So we use this switching to reduce the number of double pairs by exactly 1. And similarly, you can do something to reduce the number of loops by exactly 1 and make this kind of unimpressed face that we have here. But again, these pairs should all be simple pairs with multiplicity 1. Okay. So the idea of using these operations, if you're doing asymptotic enumeration, is just to get an expression for the relative sizes of 2 sets. And actually, it's just double counting, because as Marta Bonamy said on Monday, is there anything higher than double counting? So Brendan McKay introduced the switching method for enumeration. And the idea is you have these 2 sets A and B, and you want an expression for the ratio of their sizes. So you define a switching operation that turns elements of A into elements of B, and you make an edge for each possible application of this switching. This gives you what you might call the big bipartite graph. And we're just going to count the edges of the big bipartite graph in 2 ways. And if you're lucky, there's a fairly uniform expression for the number of ways to apply the switching to each element of A. Maybe there are dA ways. So that's the degrees over here are roughly dA with some small error. And there might be a relatively uniform way of creating each element of B using this switching. So maybe there's dB ways with some small error. So this is essentially an out degree and an in degree, if we think of it oriented from A to B. And if that happens, then you can just get this nice expression for the ratio of their sizes. And if you can't get a uniform expression, you can use the expected degree on one or other of the 2 sets, right? So this is just double counting, but you can apply this over and over again, and you can have many different switching types that you analyze all in one go. And so there are some quite sophisticated theorems that Brendan has written with some co-authors to allow very complicated switching arguments. But we're going to do a relatively simple one. So how is this used for enumeration first? We're going to define a set of good configurations, always with the given degree sequence, We say that a configuration is good if it has not too many loops, not too many double pairs, and maybe, let's say, no pairs with multiplicity 3 or above. And you choose these cutoffs N1 and N2, so the probability that a uniformly chosen configuration is good is close to 1, as close as you want it to be. Usually some constant multiple of the expected number of loops and doubles is roughly what people use. Then this means that the number of good configurations is asymptotically equal to the number of all configurations, which is something that we can just write down. It's a known quantity. Now, taking any good configuration, it has some number of loops and some number of doubles. You can apply the loop removal switchings to remove loops one at a time, and then apply the double removal switching to remove the double pairs one at a time. And eventually you will get down to a simple configuration, and that's the set we want to know the size of, the number of simple configurations. And each time you do one of these switchings, you get a ratio of the sizes of the corresponding sets, and by multiplying things together and adding them up in the right way, you end up with an expression for the number of simple configurations in terms of the number of good configurations, which is asymptotically equal to a known quantity. So that's the whole thing. It gives you an asymptotic enumeration formula as long as the maximum degree is not too large. So that's essentially the argument of an enumeration result of McKay and Warmold from 1991. But in a paper that was published the year earlier, they showed how it also gives an algorithm based on these switchings. Okay. So you start in the same way as for the configuration model by generating a uniformly random configuration. And this time we only reject it if it's in the bad set, which is the complement of the good set. So if it's not good, we reject the whole thing and start again. And now we know that it doesn't have any triples or higher. It's got maybe some loops and some doubles. And we repeatedly apply the switchings. First, we get rid of the loops, then we get rid of the doubles. But for every switching step that we propose, we introduce a rejection probability. And the rejection probability is calculated carefully so that if the state before is uniformly distributed over its set, then it will be also after the switching. And the point is that the first one you choose is not only uniform over the good set, it's also uniform over the set of all switchings with the same number of loops and doubles as it. Is that a question? No? Okay, so if you can get this working with the rejection probability, then in the end, you'll have a uniformly random configuration with no defects, a simple configuration, and the corresponding graph will also be uniformly random. So I need to tell you, or I want to tell you how we preserve the uniformity. How do we choose the rejection probability? And let's just focus on the switching that removes the double pairs. That's the most important one, actually. So we'll assume we have no loops. We have no pairs with multiplicity greater than 2, and we've got precisely D doubles, and this set is called SD. This is also the reason I use D throughout my survey for this, to preserve D for this. That's why I use K throughout my survey for the degrees, in case anyone was wondering. So anyway, for a given configuration with D doubles, we let F of P be the number of double removal switchings that can be applied to P, which is like its out degree in the big bipartite graph. And for any set P prime in S of D minus 1, B of P prime is the number of ways that you can produce P prime using a double removing switching. So that's like the in degree. For every element of SD, we also need an upper bound on its out degree and a lower bound on its in degree. These don't have to be tight, they just have to be convenient. So we have to find these expressions that just depend on D. And then you can define the rejection probability for a proposed switch from P to P prime exactly like this. It's 1 minus the product of the ratio of the out degree of P divided by its upper bound times the inverse of the in degree of P prime divided by its lower bound. And if both of those ratios are close to 1, then this whole rejection probability is close to 0, which is what we really need it to be. Now, let's prove that this choice of rejection probability preserves uniformity. So let's assume that P is uniformly distributed over SD and we've proposed a particular switching, and we're assuming that that switching will not be rejected, then what's the probability that the next state is p primed? So the probability that the next state is p primed is a sum over all of the possible elements p which could produce p primed using a double switching, sort of the in neighbors of p primed. We need the probability that we were at that particular p before, but that's just uniform by assumption. And then from that p, we have to choose the correct switching that's going to take us to p primed, which is 1 over the out degree f of p. And then this last expression is 1 minus the rejection probability, because we're assuming that we did not reject. And so you can see we get some nice cancellation. Some factors can be taken out to the front of the sum. And now we're summing over the in neighborhood of p primed 1 over its in degree. So this remaining sum is simply equal to 1. That's why we chose the rejection probability that way, because the probability that we see p primed is completely independent of p primed, which means that conditioned on not rejecting that proposed switch, we have got the uniform distribution at the next step. Okay, so this is how the McKay-Warmold algorithm works and why the output at the end is exactly uniform over the target set. Now, McKay and Warmold proved that the expected runtime of their algorithm is k max squared m squared under this condition that the maximum degree is order m to the 1 quarter. So m is the sum of the degrees, or if you prefer, you can just think of the number of edges here because it's inside a big O. In the regular case, the condition becomes the degree is order n to the 1/3, and the expected runtime can be improved to k cubed n. Yes. But if the maximum degree gets any larger, you get too much variation in the degrees in the big bipartite graph, and that leads to the rejection probability becoming too high. So it is a barrier to improving this any further. Okay. Cool. So new ideas were needed to get beyond this particular barrier. And those new ideas were brilliantly provided by Jane Gow and Nick Warmold in 2015. They were able to extend the algorithm to still give exactly uniform sampling. First, they focused on the regular case, right up to degree little o of root n. So from order n to the 1/3 to little o root n, which is actually a big jump. And the expected runtime is the same as what McKay-Warmold achieved in the regular case. Okay, so their first idea was to split the rejection probability into sort of 2 parts and think of those 2 parts separately. There's an F rejection that depends on the configuration you're coming from. And then there's a B rejection, which depends only on the configuration that you arrive at. And F here is for forward and B is for backward. So it's always the case that the number of double pairs is higher than the number of loops in expectation. So these are the ones that cause us the problems. Jane and Nick actually allowed some triple pairs in their good set, but these are also not too numerous. So you can just switch away the loops and switch away the triple pairs using exactly the ideas from McKay-Warmold. So the new ideas were only needed for the double pairs. Okay, so we're now going to focus on just removing the double pairs. And so we're going to use the set SD again, where we have precisely D double pairs and nothing else is going wrong. Okay. So we still have the switching from before that we used to remove doubles with exactly the same interpretation here, removing exactly 1 double and not doing anything else. And now we call this a type 1 class A switching. So Jane and Nick described their new scheme very generally, and every switching will have a type and a class. Okay, the first idea is, if I propose this place to do a doubles removing switching, but I happen to already have a pair between these 2 cells, then in the McKay-Warmold algorithm, I would reject that because when I switch, I would introduce a double pair here. But to reduce the probability of F rejection, I can just allow that switching to take place. And that is called a type 1 class B switching. So the class changes here. These actually preserve the number of double pairs. So they go from SD to itself, but the double pair moves around a little bit. So if one of these 4 potential places where a pair might be does have a pair, then this is a type 1 class B and we allow it to happen, okay? And this is successful for reducing the probability of F rejection. But it also causes a new problem when you look at the in degree, the number of ways you could create this object, because these things vary too much if you look at all of the elements of SD, and that would lead to a high probability of B rejection. So to deal with this problem, Gowan-Warmold did something quite counterintuitive. I think this is like, I don't know how they thought of this, I guess, but they actually introduced a new switching, which is called a type 2 class B switching, which introduces the number of, increases the number of double pairs by 1. So now we allow these 2 or these 2 pairs of cells to already have a pair between them, as I've shown here, and the number of double pairs goes up by 1, which seems odd because our overall aim is to get down to S0 where we don't have any double pairs at all. But we will only perform this switch with a low probability, so it won't happen very often. And why do they introduce this? They call it a booster switching, and they do it because if you look at the number of places where you see either this configuration, this subconfiguration or this one on those 3 cells, that number doesn't vary too much over a given SD. So it makes things much more uniform, and that leads to a lower B rejection probability. So those were the ideas that they used. I see a raised hand. Do you have a question? A quick question.
Can you hear me?
Yes,
can you hear me, Catherine? So you mentioned, what is the name of this switching?
This one is a type 2 class B.
And you mentioned it is somehow strange, or?
Oh, I find it strange. You don't have to find it strange.
But it is if you look at the language of category theory, it is somehow called cylindrical switching. So it is in a higher level. We can talk about it later.
Okay, thank you.
You're welcome.
All right. So these are the ideas that Gowan-Warmold used, and this is the picture now. Instead of just having switchings that march down all the time, we have 3 different ways of coming into the set SD. Okay, I'll also note that the F rejection probability just depends on P and the type of switching, while the B rejection probability depends only on P primed, the target, like the endpoint, and the class of the switching. Okay. To fully specify the algorithm, we need one more thing. We need to introduce some parameters rho tau of D, which says if I'm in SD, what is the probability that my next switching will have type tau? And we want these to add up to something less than or equal to 1. So they might not quite be a probability distribution on the types. There might be a little bit of sort of probability left over, and we just turn that into a rejection, another rejection probability. So in order to set these, satisfying some conditions that I'll hint at in a second, you have to show that there's a solution to a system of inequalities. Okay, let's assume we've done that. Now we can tell the algorithm. We've already got rid of any loops and triples that we might have had before, and we're at some element of SD. If D is 0, you output the corresponding graph straight away, which will be a simple graph. Otherwise, we're going to choose the type tau according to this almost probability distribution rho, and choose a random type tau switching from P to P primed. And this will determine the class alpha of the switching once you know P primed. Then you perform your F rejection and B rejection with the appropriate probabilities. And if you don't reject, then you just move to P prime and you repeat. And that's the whole algorithm. Okay. So how do we know we get a uniform output? Well, the invariant is no longer that we maintain a uniform distribution at each step. That doesn't work. Instead, Jane and Nick said the goal should be this. I've written over the whole algorithm, but actually it's over the doubles removing phase of the algorithm. So we want to ensure that the expected number of visit to each configuration in SD, D doubles, over the doubles removing phase when we're bouncing around up and down, that expected number of visits should only depend on D and be independent of the particular configuration P. And if you can achieve that, then when you get to S0, since you exit straight away, as soon as you hit S0, you're going to be uniformly random over S0. So that makes it work. Okay. And as I said earlier, they get an expected runtime order k cubed n up to k is little over root n. Okay. They also said, look, if you forget about the class B switchings and you never perform any rejection, then our analysis tells you that you will get an asymptotically uniform output and the runtime is fast. It's order kn. So this is as fast as the configuration model in that case, but up to k equals little o root n. But of course, the output is not exactly uniform. It's asymptotically uniform. Next, Gao and Warmold looked at power law degree sequences, which have so-called heavy-tailed degree sequences where most vertices have a very low degree, but a few vertices have an exceedingly high degree. The number of vertices with degree, at least j, is proportional to j to the minus gamma for some exponent, gamma between 2 and 3. I think that's roughly it. And if the exponent is slightly below 3, I think they can handle 2.88, something, then they have an algorithm for exactly uniform sampling of these graphs with expected runtime slightly higher than quadratic, which is pretty cool. And then another big breakthrough just a couple of years ago, Arman, Gao and Warmold got the runtime of these algorithms down even further. It turned out that the most expensive part was the calculation of the B rejection probabilities. So when you choose where to do the switching, the F rejection probabilities kind of take care of themselves automatically, but the B rejection probabilities you have to calculate. And what you do, and that has to be exactly accurate, otherwise you don't get exactly uniform switching. I mean, distribution. So the way you do it is you need a database of local structures, these little local structures around every vertex, how many there are, and you need to maintain this as you perform each switching. Whereas Arman, Gao and Warmold said, if we do this incrementally, bit by bit, we can get away with a much smaller data structure, much less information being stored around each vertex, and it's more efficient. So this is what they're able to achieve. In the regular case, under the same conditions as Gao Warmold, they got the expected runtime down to kn plus k to the 4th. So this is essentially linear in the number of edges, or else it's this k to the 4th. The power law algorithm of under the same conditions on gamma, they improved to linear, which is kind of amazing. The power law algorithm, I forgot to say, it's much more complicated than the Gao-Warmold algorithm. There are many types of switchings and many classes, and there's a lot going on. Okay. They also looked at the McKay-Warmold algorithm and showed that it gives, using incremental relaxation, you get order m expected runtime under the same condition, k max little o m. So that's for irregular degree sequences, and a result for bipartite graphs under similar conditions or the same conditions really as this. Okay, so if you want to sample some, to generate some random graphs and they fit into these categories, then you should probably be using these algorithms, especially if it's a regular or an irregular sequence that satisfies these conditions, because C code is available from Nick Warmold's website. So that's pretty cool. Okay. Before I leave the area of the switching spaced algorithms, I want to tell you about an algorithm from Svante Jansen in last year, or published last year. This is also an algorithm that uses the switching method applied to random configurations, and it also aims to remove defects, but it's different in a couple of ways. So it's using slightly simpler switchings than the ones that I was just telling you about. You can see there's one less pair involved in each of these switchings. But more importantly, maybe, is that Jansen uses these in a much more relaxed sort of, he's much more laid back about how you use these. So this has to be a loop, but we don't insist that this is a simple pair. This might be part of might have multiplicity 7 or something. We just don't care. We also don't insist that these are 3 separate cells. So what you introduce over here might be a loop. It also could be part of a multiple edge. We don't care. So we don't care whether there are any pairs here. So it's anarchy, really, compared to the Gao-Warmold algorithm. Really anything goes here, apart from the fact that you're definitely targeting this loop. And similarly here, we're targeting these two pairs, which those pairs have multiplicity at least 2. So there might be several other pairs between these two cells. We don't mind. We're just choosing 2. And this might be a mess, and there might be stuff here. So you can see that there are many fewer rules to apply these switchings. You might fix more than one defect at a time, and you might introduce some more defects. But Janssen proved that if the maximum degree is little o root n, the sum of the degrees is linear, and the sum of the square of the degrees is at order n, so at most linear, then the output of this algorithm is within total variation distance little o1 of uniform. So it's very close to uniform, it's asymptotically uniform, and with high probability, the runtime is order m. So that's as fast as the configuration model. And this just works because under these conditions, the expected number of switchings that you would actually perform is just a constant number. So there's really not that many defects that you expect, and you can just get rid of them quite easily without introducing many more. So that I think is a very cute algorithm. And while we're on the subject, before I start talking about Markov chains, I want to make a remark because it's going to come up again later. So these simpler switchings that Janssen used in his algorithm had been used before by Brendan McKay in a very early application of the switching method for asymptotic enumeration. So there he was using the stricter interpretation where these are simple and blah, blah. So we're removing exactly one loop and double, but these operations are the same. Same pictures. And the way that Brendan and Nick made a improvement on the range of degrees that could be handled to give an enumeration formula was, instead of using these simpler switchings, to make them slightly more complicated. So they realized that using the slightly more complicated switchings allowed them to extend the range that they could enumerate over to allow for a higher maximum degree. So that's the takeaway message here. Sometimes using slightly more complicated operations allows you to do more. We'll see that come up again shortly. Okay, so now we're going to talk about Markov chains. So in case you need a reminder, a Markov chain is a stochastic process which just decides what to do next based on where it is and not how it got there. And really all of the algorithms I've talked about tonight, or this morning for you, maybe, are Markov chains. But these ones that I'm going to focus on now have the uniform stationary distribution over the target set. I want to assume that my Markov chain is time homogeneous, which means it doesn't look at its watch when it decides what to do. It just always does the same thing. So you can put the transition probabilities into a matrix P called the transition matrix. That really holds all the information about the chain. I also want the Markov chain to be ergodic, which basically means you can get from any state to any other state in the state space, which is the underlying set that you're walking on, using steps of the Markov chain. So the underlying graph is connected and you don't have any weird periodicity issues. And that guarantees that you have a stationary distribution and you're converging to your stationary distribution. And my final assumption is that the stationary distribution is uniform, which you can achieve by making P symmetric. So this Markov chain is sort of as nice as you could hope for, really, in terms of having these lots of nice properties. And now we say that a Markov chain is rapidly mixing if it converges to within some epsilon of uniform in total variation distance in time, which is polynomial in the logarithm of the size of the state space and the logarithm of the inverse of this tolerance epsilon. So the user gets to choose how small epsilon is. And you can get within exponentially small tolerance in polynomial time. I've put m here because for us, the logarithm of the size of the state space is m log m. So we may as well say polynomial in m. And so now what I would really like is an ergodic, rapidly mixing Markov chain on G of k with uniform stationary distribution. Okay. The first people to apply the Markov chain approach to sampling graphs with given degrees was Jerram and Sinclair back in 1990. And they did this because they had a Markov chain which they knew how to use for sampling perfect and near perfect matchings of a graph. And using a construction of Tut, you can reduce the problem of sampling realizations of a degree sequence to sampling perfect matchings of a particular graph. So that's how they got the idea to work on this problem. Here's a graph with the given degree sequence, and this is what the Jerram-Sinclair chain does. For a transition, you choose a pair of vertices, an unordered pair of vertices. And if, as in this case, they happen to describe an edge, you just remove it, assuming this is a graph with the given degree sequence K. And now what we have is a graph which almost has the degree sequence K, except two vertices have got a degree deficit of 1. Now we choose another pair of vertices. This time, one is a degree deficit vertex and the other one isn't. And I'm allowed to have a small degree deficit, but I'm not allowed to have a surplus. So even though I would like to add this edge, first I have to remove a randomly chosen edge which is incident to 6. So maybe I remove the edge 4, 6 and insert 2, 6, and now my degree deficit vertex has moved across to 4. And if you happen to choose two vertices, which are the degree deficit vertices, you can join them by an edge, and that brings you back to the target set GK. So what you can see is this is walking around not just on GK, but also on graphs with a slightly different degree sequence to K. In fact, the degree sequences that you see range over this set of all graphical degree sequences, which are sort of entry-wise less than or equal to K, and at Manhattan distance at most 2 from K. So that means it's either K or two vertices of degree deficit 1 or one vertex of degree deficit 2. So you run the Jerram-Sinclair chain for some number capital T steps, and capital T, you know, is the distance from uniform is at most epsilon. You look at your final graph. Does it have degree sequence K? If not, you have to do rejection sampling. So you go back and start again. And so the expected number of trials until success is approximately the ratio of the sizes of the large state space to the target set that you really want. Approximately, because the Markov chain is only doing approximately uniform sampling. Okay, so it makes sense to ask that this ratio is polynomial. And so Jerram and Sinclair said that a family of graphical sequences is p-stable, polynomially stable, if you can find some polynomial little p such that for all degree sequences of length n in that family, the size of the larger state space is at most polynomially bigger than the size of the original set, okay? And if you have a p-stable family, then the Jerram-Sinclair chain is rapidly mixing for any graphical sequence in that family. And intuitively, p-stable sort of says that these small perturbations to the degree sequence don't massively blow up the number of realizations, okay? So what if you wanted a Markov chain that didn't leave the set G of K, that only walked within G of K, so that you don't need to do this rejection sampling at the end? Then you might look at the switch chain, which is the simplest thing you can do to satisfy these requirements. So you choose a pair of non-incident edges randomly and replace them by a pair of edges without changing the degree sequence. So you could put the same edges back, or you could rewire them like that or like this, and you choose one of them randomly. Clearly, if you do this lots of times, you're going to mess up the graph and you'll forget almost everything about the graph. You'll be very close to the uniform distribution. So this was, it's a very obvious and simple small change to do to a graph, and it has arisen in many contexts, and in particular Diaconis had used it to look at sampling contingency tables. The first people to look at it for sampling graphs were Cannon, Totali and Van Paula, who looked at bipartite graphs, but unfortunately there was a bug in their proof. So, I forgot to say, the switch chain is ergodic and its stationary distribution is uniform, so it's a good candidate for us to do sampling over GK. Here's a lovely slide with a list of results where people proved the switch chain to be rapidly mixing in certain situations. With Colin Cooper, Martin Dyer, and myself, we looked at K regular sequences for any degree from 3 all the way up to, n-3. And then I extended this to directed, regular, graphs. Miklos, Erdos and Sukup looked at half regular bipartite graphs where one side of the bipartition is regular and the other side didn't have to be. We were all using a framework called the multi-commodity flow method, but they used a different flow to the one that we'd been using. Later, I figured out how to generalize our regular argument to irregular degree sequences, at least when the maximum degree wasn't too large. And then together with Matteo Sfragaro, we looked at directed degree sequences and did the analog there. I'm going to tell you a bit more about this shortly. And then there was some other related work. Edish, Kiss, Miklos and Sukup showed how to turn this into a self-reducible problem so that the sampling could do approximate counting as well. And this paper takes 2 degree sequences which are known, for which the switch chain is known to be rapidly mixing, and shows how to turn them into a new degree sequence for which the switch chain is also rapidly mixing. So that was kind of interesting. Now, apart from those last 2, all the dot point proofs for the special cases, they all use this multi-commodity flow method of Alistair Sinclair, and the proofs are kind of long and technical and very fiddly and baroque. The upper bounds that result are also, while they're polynomial, which is good, they are very high degree polynomials, and so they're not very helpful to real world people, and they're probably very far from tight, but theoretical computer scientists are happy with polynomials. So I thought I should be honest and put one of my polynomials on here for you to have a look at. So this is from the first paper. Actually, the one we first published was slightly lower than this. We had a small error that we corrected and we ended up with this. So this is n to the 9th, even if k is constant. But if k is constant, you wouldn't be using this method, you'd be using the configuration model. So this is really not good. Okay, but polynomial. So I want to say a little bit about how I got the extension to irregular degrees, which first appeared in a Soda paper. When I was trying to do this, it takes a while to define the multi-commodity flow, and luckily the whole definition just worked for irregular degrees, so none of that had to change. And then you look at the analysis step by step, and there were many steps, and luckily almost all of those steps also did not rely on regularity. It was some sort of miracle. There was just one critical lemma in this proof where we really used the fact that the degree sequence we had was regular, and it was to count something called encodings. And an encoding is used to try to bound how much flow in your multi-commodity flow. I'm not really telling you any definitions, but how much flow is going through a particular transition. So this is what an encoding is. It's almost an element of G of K, a graph with the given degree sequence, except it might have, in our case, up to 4 defect edges, and a defect edge is labeled -1 or 2. But you still want the sum of the labels on the edges to add up to the given degree sequence. And a standard edge just has label 1, and a non-edge has label 0. So this vertex, the numbers in brackets are the required degrees. This wants to have degree 2, and it's got 3 normal edges and 1 defect, but the defect is labeled -1. So 3 minus 1 is 2, and so that's why this works out. You can also see that if you remove the defect edges, what you have left over is a graph with a perturbed degree sequence. It's almost got degree sequence K, except there are some things that have been messed up. So there's a connection there. Okay. So in the 2007 paper, for the critical lemma to count encodings, we showed that every encoding was at most 3 switches away from a graph with the correct degree sequence. And that allowed us to sort of count the size of the encodings relative to the size of G and K. And we were really doing a switching method sort of enumeration. In particular, to get rid of a -1 defect edge, we wanted to choose 2 incident edges here, such that these other neighbours, U and V, are not adjacent, so that you can take away these 2 edges and increase the labels here and here. So -1 becomes 0 and 0 becomes 1, and you end up with this. And to prove that we had always a choice of U and V, we were using regularity. But for irregular K, there may be no valid choice for U and V at all. And that was the stumbling block to extending this argument to irregular graphs. But what I realized with my knowing what happened in asymptotic enumeration is that if I used a slightly more complicated switching, I could get it to work. So here was use a slightly more complicated operation and expand what you can do. Okay, I think I might be almost over time. I just want to say a couple of little things. So there was some really nice work by Amanatidis and Clear. They gave a definition of a strongly stable degree sequence. And a sequence is strongly stable if it's pretty close. It's, what do I want to say? For any element of the state space of the Jerram-Sinclair chain, the bigger one, it takes at most B moves to get to an actual graph with the correct degree sequence. And B is some constant. If you're strongly stable, you're P stable, and they prove the switch chain is rapidly mixing for all strongly stable sequences. And they prove something similar for bipartite graphs. And this actually captured everything we knew about graphs and bipartite graphs in terms of mixing. I was involved then more recently in a similar result where we proved that any P stable degree sequence gives a rapidly mixing switch chain for graphs, bipartite graphs, and directed graphs. Jane Gow and I introduced yet another notion of stability, an easily checked sufficient condition, which was tailored to power law degree sequences and other heavy-tailed degree sequences. And so this gave, for the first time, a proof that some of these power law degree sequences are P stable and the switch chain mixes rapidly for them. And if you're interested in encodings, stability, a little bit on the multi-commodity flow proof, I talked about this in more detail in a recent seminar. And if you look on my webpage, you might find a link. Okay. If there is a barrier to rapid mixing for the switch chain, we know it's not P stability. This was observed by Jerram-Sinclair and McKay back in 1989 and has been generalized recently by Erdős and his team. They gave a family of non-P stable degree sequences for which the switch chain mixes rapidly. I'm nearly finished. Can we have some practical mixing time bounds for the switch chain, please? Tikhomarov and Yusuf says, yes, you can for the switch chain on K-regular bipartite graphs. So this was about a year ago. This paper went up on arXiv. You can see the bound is quadratic in the number of edges. So this is a really, really huge improvement on what was known before. It's a very technical argument. They establish a Poincare inequality to bound the eigenvalues of the chain directly. Whereas when we use multi-commodity flow, we're sort of tiptoeing up on the eigenvalues and introducing lots of factors of n along the way. Okay, some open questions. Are there graphical sequences for which the switch chain is not rapidly mixing? We don't know. Can this very new and very impressive approach of Tikhomarov and Yusuf be extended past bipartite regular graphs? And can we find any algorithm which will efficiently sample graphs uniformly or almost uniformly for any graphical sequence K? And that's it. Thank you very much.
Well, thank you very much, Catherine, for a very interesting and enjoyable talk. Let's all show our unmute and show our thanks. And are there any questions?